Okay, hello everyone. There's no slide. There's no slide. No. No slides. Right. What I'm gonna show you today is this little thing that I did. I hope everyone can see that at the back. So this is a magnetic hose, and its purpose is, in general sense, include magnetic fields in places where it shouldn't be. So taking a step back, my name is Fernando. I'm working in Q-Group, a group in CQT that works with 3D superconducting devices. And in general, our experiments involve lighting qubit circuits inside superconducting enclosures. And that has a good and a bad side. The good side is that the superconductor, it protects our circuits from external noise, from spurious electromagnetic fields. But at the same time, this is a bad thing because it also blocks control magnetic fields that we could use to change the frequency or the properties of our circuits. So our approach to overcome this problem is to poke the device, the enclosure, with the magnetic hose. And on one side, of course, goes the circuit, and on the other side, we put a small coil to provide the magnetic field. And I'm so excited to talk about this with you because it's not just a straw, it's not just a hole that you make in the cavity and you put a coil on one side, because that would actually not work, because the field would decay very quickly. And for that reason, this coil, this hose, it's made of 11 concentric cylinders. When you come to my poster, in the post section, I'll show you this in person. And it's made of two materials, mu metal and aluminum. The purpose of the mu metal, since it has a high permeability, is to push the field forward. While the aluminum, it blocks the field from going sideways. So it doesn't curl back to the coil until it has reached the end of the hose. So we have maximum transferability of the field from one side to the other. And there are just so many design considerations and small details going into this, and it's such a weird size, as you cannot see, that I have to do with my own hands, but I cannot see with my own eyes. I have to use microscopes, and it's very delicate. That I'm actually very surprised that we got this in our second attempt. And we already demonstrated full tunability of a superconducting circuit, and even though we used a very small coil for that, very weak source, and included only moderate disturbance to the field, to the system. And we're already excited to include this in new architectures, to use it, for example, to control bosonic modes inside high-Q cavities, superconducting cavities. And sadly, my time is running up. It's probably gonna bring it any second. But I wanna hear your opinions about it, your ideas. I wanna show you this in person, so I'll be waiting for you at the poster section.